So we're going to start with the pH of strong acids and bases. Before you do any of these problems that I have listed on the board, strong acids, bases, weak, salt, buffer, or invader problems, the crux of all of that is being able to identify what you have. So I'm always going to say, what is it? What is it? What are we starting with? What are we starting with? To the point you want to punch me, because we have to know what we're starting with in order to know what process to take. So looking at these first two problems, we're finding the pH of strong acids and bases. So it's number 7 right here. It says, calculate the pH of a 0.450 molar HCl solution. Classify. What is that? Strong acid. So these are really easy problems, and I'm going to show you why. Why is an acid strong? What makes an acid strong? It completely ionizes. So we're going to have this single-headed arrow, and it's going to make that. Okay? Now, if we're looking for pH, what are we actually looking for the concentration of to solve for pH? That guy, the H plus or the H3O plus. So they didn't give us that. What they gave us was the concentration of the HCl. So how am I going to find the concentration of the H plus? Well, because it ionizes 100%, if all of these, if we have 0.450 moles of those in a liter, we're going to then have 0.450 moles of those and 0.450 moles of those, right? So in the case of a strong acid or base, you're allowed to just straight up take the negative log of the acids or bases concentration, because that is equal to the H plus or the OH minus in the solution. All right? So here we get the negative log of 0.450. So I need your calculators. We need to move quick, because I think my mic's not going to make it. And give me a pH then with 3 sig figs. 0.347. All right? 3 decimal places is 3 sig figs in pH world. All right, now let's do the next one. Calculate the pH of a 0.710 molar KOH solution. Classify. Strong base. This other one was a strong acid. All right, so since this is a strong base, again, you don't have to write this equation out every time. I'm literally just trying to make you aware that they're only giving us the concentration of the KOH. In order to find the pH, we need the concentration of the OH, which is going to be the same due to the 100% ionization. If I take the negative log of this 0.710, what am I actually solving for? POH. Good. So give me POH to 3 sig figs, please. 0.149. Is that what they're asking for in my problem? No. What do they want? pH. So how do I find that from POH? 14 minus that will give me my pH to 3 decimal places. 13.851. A lot of students skip this step. A lot of students go, oh, they get negative log happy. Negative log of blah, and then they stop. And they're like, done. No, that's not the pH. That was the POH. So you need to ask yourself, does it make sense? Does my value that I calculated make sense? If I'm looking for a pH of a strong base, what range of numbers should I be getting? 7 to 14. The fact it's strong, we're going to get really high up there. It's going to be really, really close to the 14, 12, 13, 14 range. So that's going to make sense. So ask yourself, does my answer make sense before you move on? And that's all it is. Take the negative log of the concentration of the acid or the base, and that's going to give you the pH of the solution for strong acids and bases. Ready to move on to weak? All right. When we're dealing with weak acids and bases, they don't ionize 100%. So how did you write those dissociation equations on Friday? What did we put in there? That little double-headed equilibrium arrow, right? So that's going to allude to the fact that we're going to need to use Rice tables in these problems. All weak acids and bases, because they are at equilibrium, all have their own K values. What do you think we call a K value for an acid? A Ka. Good. And we call a K value for a base a Kb. So we're going to use Ks just like we did before. And these are actually easier problems because there's no coefficients, and we always shift to the right. All right? So we're going to go ahead and set up a Rice table. Now, the one rule I do have is when you are doing weak acids or bases, I forever and always want you to add the weak acid or the weak base to water and put them in the Rice table that way. Your textbook, you'll see sometimes they just split it into ions. and you don't add it to water, and then sometimes you have to add it to water. So rather than us deciding when to do one or the other and make things really confusing, that's just going to be our rule. You always add your weak acid or base to water and put it in a rice table. So the only thing different from this to last unit is you have to come up with that reaction, which is easy because here we're looking for the Ka value for benzoic acid. How do I know that's a weak acid? It's got carbon in it. It's got a crazy organic name. You didn't learn how to name that because it's a common name. So when you don't know the name of it, it's going to probably, whoa, HC7H5O2. It's probably going to be organic, and those are weak. So we add it to water. Now this is just a movement of an H, a Laurie-Bronsted acid-base reaction where this is the acid, that benzoic acid is an acid. What is an acid? A proton donor. So we get this plus H3O plus. That's the hardest part, is doing that. All right, our original concentration of this guy is 0.100. And to this pH here, I want you to add an O. I want it to be 3 sig figs as well so it doesn't cause any problems. All right, water is a pure liquid, so we don't include it in our equilibrium. Before any dissociation occurred, we had 0 product. Which way do we have to shift? To the right. And the beauty, again, about these acids and bases, we only have coefficients of 1 in the equation, so we never have to raise the stuff to a power because we're always just moving an H. So we never have to square, power, cube, whatever. All right? So here we get 0.100 minus X, X, and X. So if we're trying to solve for Kb, I'm going to write the expression real quick, unsubstituted. Products. Yeah, solving for Ka, my bad. Since we're solving for Ka, we're going to need to put stuff into that expression. So what would be helpful for us to solve for in order to do that? X. We need X from the rice table. Well, where the heck am I going to get it? What else did they give us? They said pH is equal to 2.59, and I added that 0. How does that help me? Perfect. If I take the negative log of the H plus concentration, or H3O plus, that's equal to my pH. So what I'm going to do is solve for that, which is my X. So 10 to the negative 2.590 give me 3 sig figs in my concentration. Ten to the negative 2.590. I need 3 sig figs. All right, so that's what X is equal to. This is 0.00257. This is 0.00257. And this is 0.00257. So when I plug all that in to my expression, Ka is equal to 0.00257 times 0.00257 divided by, what is that number, 0.1 minus 0.00257? 0.0974. All right, so give me the Ka. 7.8. And we don't need units on our Ks. That's a pretty small number. Does it make sense that it's a small number? Why do Kas and Kbs, why are Kas and Kbs consistently small? Because these acids and bases don't ionize to a great extent. Because they don't ionize much, the reaction favors the reverse. Okay? Because it favors the reverse, we're going to have way more reactants than products, so that's going to lead to small numbers. So check your work. If you're getting a K that's like 5.4 times 10 to the 50th, yeah, something's wrong. All right? Let's go ahead and do one more. We're going to do kind of the same problem, but now in the world of bases. It's exactly the same problem. This time we're finding Kb. This is a situation where you had to add it to water, and that's why I want you to always add it to water in your rice table. So classify ammonia. What is it? A weak base. We're going to add it to water. And again, I'm going to make this 366. A base is a proton acceptor, so we make NH4 plus OH minus. Our original concentration initial here is 0.100. Water's not included. Before ionization, we have no product. We have to shift to the right. And so we get 0.1 minus X, X, and X. What's a little bit different here is what we're solving for when we get our X, because what else did they give us here? pH. If I take the 10 to the negative 11.130, what am I actually solving for? That's the concentration of hydrogen, right? But what do I need? I need the concentration of OH. So there's a couple of ways I can approach it. Which way? What do you want to do? You want to subtract from 14? Okay. We're going to subtract from 14 minus 11.130. And so what do we get? Give me 3 sig figs. What, say again? I need 3870. All right. So that's going to be POH. So now if I go 10 to the negative 2.870, what do I get for X? And that's equal to my OH concentration. Okay, so 0.00135, 0.00135, 0.1 minus 0.00135. KB is equal to products over reactants. So I get 0.00135 squared. What's the subtraction of those two numbers? 0.0987? And so I end up getting a KB of, I didn't hear the first number. And that is, give me one more. Then why didn't y'all tell me 9? I see. Okay. All right. Feeling pretty easy? All right, now we're actually going to solve for pH, as what the whole goal of using these rice tables with weak acids and bases is. Looking at this, we're finding the pH of what kind of solution? A weak base. What made you say that? That's correct. Oh, but it has a carbon in it. That's acids. What? It's that NH thing. What was that called? A nitrogenous base. All right. So the fact that it's a nitrogenous base makes it weak, but there's some other indicator that this is a weak base. Ah, KB. All right, so when we're solving for the pH of a weak acid or base, we add it to water and put it in a rice table. All right, a base is a proton acceptor, so where does it accept it? It's going to make CH3, NH3 plus, and what's left over? OH minus. So we have an original concentration of 0.712. That goes out 0, 0. We're going to shift right, minus X, plus X, plus X. So we get 0.712 minus X, X, and X. If we're solving for pH, ultimately, what do we need to find to get there? X. That'll give me the concentration of OH minus, which then we can figure out POH, which we then subtract from 14 to figure out pH. So we're going to get there. We're going to set it equal to our KB, but there's something special that's important to know that you can do with weak acids and bases. This guy, because equilibrium lies so heavily that direction and so little that direction, this guy's got a pretty high concentration compared to the guys on the right side. So he's kind of like Donald Trump compared to the rest of us. So if Donald Trump, and he's up there, by the way, laying on his stomach with the dollar bill in his hand, if Donald Trump were to drop a $5 bill on the side of the road, is that going to change, mathematically affect his overall fortune? No. So we're allowed to drop that X. Now we're going to prove why we can do this mathematically in a minute, but the first time you drop it, you need to indicate to the AP people that you know this is probably mathematically negligible. You can put negligible, too small to matter, something about, you got to state that you're doing it because you think it's not going to affect the overall. These X's, though, are still important because this is me. I'll take $5. I could go buy a dinner with $5. I'm happy with that. So that is an important value to me. I can't drop every X. All right, so now, because of the fact by definition, weak acids and bases are weak because they don't dissociate. So all of them have small k values, and all of them are going to heavy-handed be on this side. So those concentrations are going to be much higher in proportion to these concentrations. The question was, how do I know it was favored left? Okay, so my Kb is equal to CH3 NH3 plus times OH minus divided by CH3 NH2. So if I plug in my X's, of course I lost my Kb. What was that value? 4.4 times 10 to the negative 4 is equal to X squared over, I can drop that minus X because it's so small dissociated that it doesn't matter. So solving for X, that's going to give me the concentration of OH minus. And what does that come out to be? To 2 sig figs. One more. No, do I want 3? Let's just stay with 2. All right, so then if I take the negative log of that, I get a POH of 2 decimals, I mean. Now, again, a lot of students will stop here and be like, oh, that's the pH. Ask yourself, does a pH of 1.7 make sense for a weak base? Does a pH of 1.7 make sense for a base? No. So you know that can't be pH. So that's going to be an indicator that, hey, I'm actually not in pH world. 14 minus that gives me 12.26. So that's the answer. Now, if you're asked to justify, you always kind of want to check this, but you don't necessarily have to write it down, but I want you to be cognizant of it. You're basically cheating by dropping that X. You know, you're making an assumption. So the way to prove the assumption is we have to check what we call the 5% rule. If dissociation is less than 5% of the original acid, then we're allowed to drop it. We're allowed to drop that X. So how we do that is we take the value for our X and divide it by the original concentration of the acid or base times 100. This is part over whole. X is how much dissociated from the original. Times 100 gives us a percent. If that percent is less than 5%, we're good. If it's not less than 5%, technically we're supposed to go back up and re-include the X, put it back in here, do the quadratic formula, and resolve for it. Okay? So we had an X of 0.018 divided by an original concentration of 0.712, part over whole, times 100. That's going to give me a percent of 2.5%. This is less than 5, so bam, we are mathematically justified in dropping that X, and we don't have to go back. No, on the AP, again, because of, now on my test you might have to, but I'll tell you, hey, find the percent dissociation. But the thing about the AP is quadratic formula being used is not going to be right now something that's going to happen because those of you with these calculators have an advantage. They can't do that unless they make that calculator or a calculator like it a requirement for the course. So you're always going to be able to drop that X. However, you still need to tell them it's negligible. Okay? The reason I am making you, in my class, solve for that X is when you get to college or you take this course, most professors are like, hell no, you're not dropping X. So I want you to have experience with it and know what's going on, because you can't assume X is to be dropped. But on that AP course exam, they have to drop it to make it fair for everybody. Or even, I should say, for everybody. Again, I will be looking for you writing negligible, mathematically negligible. And then I might say, prove this. Why is it negligible? Why are you allowed? And then you'd go and do the 5% rule and check that out. I would just make it a good practice every time you do a problem that you dropped X. Just check. How hard is it to divide that X into the original concentration, just to see? Show percent dissociation. That's it. Yep, and say less than 5%, therefore allowed to drop. All right? All right, so that's it. Now I'm going to give you time to work on your homework. The way to learn this stuff is just tackle it yourself. Remember, this is all leading to big things, so you really have to have a good understanding and this should become second nature to you, okay?